Hey everyone, I'm Ryan Verghese, and along with my teammate Neil Rajiv John, we are excited to present to you the concept of divide and conquer. In this presentation, you will learn what divide and conquer is, how to calculate its time complexity, a real life application of it, and other application in the field of computer science. This approach is widely used to efficiently tackle complex problems like global expansion of territories, warfare against a group of allied forces, and, of course, quicksort. Jokes aside, this strategy involves breaking down a problem into smaller subproblems of the same type, solving them recursively, and then combining those solutions.
Algorithm, as a term, has for long been associated to codes and techniques that may potentially break into high security biometric identity control mechanisms safeguarding Swiss banks and such sorts. I know it was too much to take in, but people think highly of algorithms. Little do they notice that algorithms are part and parcel of the smallest and most meager of activities in their lives. Similarly, divide and conquer, apart from being used by Alexander the Great, the British in India, has also been used by Tim, who is just in second grade, especially when he comes across a word like pneumono ultra. Let's just move on. Searching a given word in a dictionary makes use of the divide and conquer approach without us even giving much thought to it. So let me start with an example. Assume that we are finding a word, maybe jalapeno is the word, in a dictionary. What we do is we open the book near the middle. That's the start of the process. And the open page on the top left page, we have the word kiwi written. Now we know that K comes after J, and hence we neglect the rest of the pages which are after this particular page and only focus our attention on the pages before. Imagine you turn to another page and it shows hypotenuse. We know that h comes before j, and hence we need to go forward rather than behind. And this is exactly how we will use the divide and conquer approach in finding a word in the dictionary. So basically, in simple terms, it's nothing but a binary search done on a dictionary. You might think, how so? Because if you consider a to be the smallest of the integers, smallest value, and z to have the largest value, you can think of all this as just finding a number. And this is nothing but binary search. So now Ryan will be talking about quicksort.
Now, here is an application of the divide and conquer approach in the field of computer science, which, as the name suggests, is nothing but an approach to sorting values in an array. Now, the first approach we'll use is bubble sort, which is kind of a brute force approach. And this is a really naive way of solving the problem, as it be, as you would need to repeatedly go through the list and compare adjacent elements and swap them if they're in the wrong order. And by wrong order, I mean the larger element is before the smaller element. Now, you'll continue this until all elements in the array have been successfully sorted. Now, this approach has a time complexity of O of n square, which is really bad. So, let's think of a better approach. As I mentioned, the time complexity was O of n square. So, a better approach would be to use divide and conquer. This approach involves two steps, namely partitioning and recursion. Partitioning involves choosing a pivot element and then rearranging the elements so that all elements that are less than the pivot are placed before it, and all elements that are greater than it are placed after it. Second step involves recursion. Recursion involves applying the partitioning step recursively to the subarrays formed on either side of the pivot. This means repeating the partitioning process on each subarray until the entire array is sorted. Finally, there is no explicit combining step required as the array is already sorted in place by the partitioning process. Next, I'll show you a video of the visualization of the whole process as an array, on an array. Now, initially, yeah. So initially we will choose the rightmost element, that is 6, as the pivot, and we'll have two pointers. One would be once the role of the left pointer would be to transfer or move all the elements that are greater than the pivot to the right of the array. And the right pointer would have the role of transferring or moving all the elements that are less than the pivot to the left of the array. Now we'll continue this process until the difference between the left and the right pointer is 1. On doing this, we'll get the partition where we need to partition the array. So the we'll take the right sub array and we'll take the element that is 8 and we'll substitute it with 6 so that we can get all the elements greater than the pivot on the right side of it. Now we've got the final position of 6, and we'll do this recursively for all other partitions. Now on doing this, we have finalized the position of two pivots, that is 2 and 6. Now the algorithm would go to the left subarray of 2, which is 1, and as it contains only one element, there is no sorting required. So we'll go to the right subpart. Similarly, the left and right subparts of 4 has only a size of 1, so there's no sorting required. So we have finally sorted the left subpart of the pivot 6. Now we'll move to the right subpart. Now on doing this, we have successfully sorted all the elements in the array. Now let's calculate the time complexity. The average case time complexity of this approach is O of n log n, and the brute force approach, like bubble sort, would mostly be O of n square. Now, if none of these complexities make any sense to you, just take my word for it. The divide and conquer approach is way cooler.
Karatsuba algorithm is our last and final application for the day that utilizes divide and conquer approach. It's an alternative to standard multiplication. Standard multiplication, we all know this because we've been doing this since our childhood. But to just go briefly over it, each and every unit integer of the multiplicand gets multiplied to each and every unit of the multiplier, and therefore we get a time complexity of O of n square for this algorithm. Not pretty effective. Yeah? Now, when we head to the Karatsuba algorithmic approach, it basically implements a recursive approach of splitting the two numbers at hand into two halves, and then multiplies it recursively. So for example, let us take values x and y, and x being 146123 as the number, and y being 3,52,120. So our first process or step would be to divide x into two, the first half, which is a, and the second half, which is b. So a equals 146, b equals 123. And now, if you see, we can actually represent x in a better way in terms of a and b, and that is 146 multiplied by 10 cube plus 123. Why 10 cube? Because if you see, the number of places which is after 146 is 3, and therefore we need to multiply it by 10 cube and then add 123 to form x. And this can also be written in terms of a and b as a into 10 raised to n by 2 plus b, where n is nothing but the size of x, the size of the initial integer, which is nothing but 6. So similarly, we split y into c and d, c being the first half, that is 352, d being the second half, 120, and we get a similar expression for it. Now, so in our next slide, what we are doing is that we take the product of x and y and we take the product of their representative forms, which we saw previously. And when we do this, if you compute over here with me, it'll be the first term of x and the first term of y, which is AC multiplied by 10 power n by 2 into 10 power n by 2, which is 10 power n. So it gives AC into 10 power n plus the first term of x multiplied by second term of y would be AD multiplied by 10 power n by 2. Then BC multiplied by 10 power n by 2. Take 10 power n by 2 as common over here. So we get AD plus BC multiplied by 10 power n by 2. And finally, we are stuck with BD. So we get plus BD. So on analyzing this answer, we have basically found out a relation between x and y, the product of x and y, and we have displayed it in terms of A, B, C, D. And if you see carefully, there are four different multiplication procedures happening. One is A into C, second AD, BC, and BD. But the Karatsuba algorithm has something up its sleeve. It reduces the number of multiplication procedures by one, since it calculates AC and BD, but does not individually calculate AD-BC. Rather, it calculates AD plus BC together. This is done using a simple arithmetic manipulation, which we can see over here. So A plus B, that is the sum of A and B, and multiplied by C plus D, we do that and we get AC plus AD plus BC plus BD. And what do we need? AD plus BC. So we take that, we need to subtract AC and BD from that. And since we have already computed it, we get the answer as AD plus BC. And so Karatsuba is doing the same job, but with one less multiplication process. And therefore, the order of a Karatsuba algorithm is order of n raised to 1.59, which is far better than the standard multiplication, which is of O of n square. And this does heavily change the game when it comes to large size values. If you see here, there's nothing but the Karatsuba function, which takes a comma c first, as you can see over here, according to the expression as well. Then it takes b comma d, since we need that also. And the last value which we require for our algorithm is a plus b comma c plus d, and then we do minus ac minus bd to get ad plus bc. So let's go on and see a recursive analysis of this algorithm. As previously mentioned, x and y are there. They're divided into a, b, c, d. K of 146, 123, comma 352, 120. So we take k of a, comma c. So it becomes k of 146, comma 352, if you remember. So it should be here any moment. Yes. So k of 146, comma 352. We again, since it's a recursive function, we have to again recursively split it into two. So it becomes 14, comma 6, 35, comma 2. We take a, comma c only. So it becomes k of 14, comma 35. And yes, so one may wonder, when do we stop this? So we stop it as soon as the value goes less than 10, since those are unit integers. Now if you see over here, we've got k of 1 comma 3, because that's the a comma c, first part of the values, a comma c. Then we have to calculate for k of b comma d. So that is 4 and 5, the latter half of the numbers. And then we add these two. So it'll be 1 plus 4, that is 5, k of 5, comma 5 plus 3, that is 8. And therefore we get over here, should be here somewhere. Yes, there you go. There you go. That's the answer, 40. But remember, 40 is not our answer, because that is the value of k of a plus b into c plus d. And what do we actually need? We need ad plus bc. So we subtract the values necessary, and then we get a final value 490 after putting it in the expression. And that is nothing but 14 multiplied by 35. So we have successfully found out the multiplication of this step. Similarly, we go back into the this recursive process, and we find k of b comma c, b comma d over here, that is 6 and 2. And since it's already single digit values, it would be nothing but 12. Yeah, let's wait for that. There you go. 6 and 2, which can be computed as 12. And then again, a plus b, comma c plus d, which is nothing but 14 plus 6, 20, and 35 plus 2 is 37. We do the same steps again and again. So basically, we are just finding k of a, comma c, and then k of b, comma d, and then lastly k of a plus b, comma c plus d. And at this point, I would like to bring to your notice that over here there's an n value also. So n value is always the the size of the numbers that are being used in the function call, which is over here 2, since k of 20 comma 37, 20 is 2 digit, 30 is 2, 37 is 2 digit, so therefore we get n is equal to 2. And yeah, that is all I needed to highlight over there. So we get our values, we calculate it, we put it in the expression, we get 740, and then we use these three values, we put it in the function again, and as you guessed it, the n value will increase to 3 since there's 3 digits over here: 146, 352, and then we get a value of 51,392. So recursively this process keeps going on. We find out for now k of b comma d, which is 123 and 120. Then we do k of a plus b comma c plus d. Finally, we get a value of 51 billion, and the calculator says so, so we believe. Yes. In conclusion, divide and conquer is a highly efficient way of solving complex problems by breaking them down into simpler ones. Anyways, too much chit chatter. Let's go into this. Knock knock, Ryan.
Who's there?
Recursion.
Recursion who?
Knock knock.
Who's there?
Recursion.
Recursion who?
Knock knock. I'm kidding. I'm kidding. This joke would have been a running joke lasting an eternity. Get it? All we want you to learn is that recursion always needs a stopping condition, and in our case, it comes in the form of a time limit for our video presentation. These are our allied forces, the resources that we used for our presentation, video presentation. And thank you. That is our presentation.